Good morning. I'd like to begin talking about our third semester calculus topics today. To start with, for now, all of our work is going to be in the two-dimensional Euclidean plane. I'm going to imagine that I've set up a coordinate system and I have 2 points in the plane, which for now I'll just call P and Q. P is here. It has x-coordinate 4 and y-coordinate 2. Q is here. It has x-coordinate 11 and y-coordinate 5. What I mean by the vector from P to Q is just an arrow that starts at P and ends at Q. I draw the arrowhead at the place where I stop. So in the usual language, P is the initial point of the vector, Q is the terminal point. The vector from P to Q, which I'll symbolize with the initial point, the terminal point, and an arrow to remind myself it's a vector. This symbol means this entire arrow. This arrow has a magnitude or length or norm as it's called, which is just the distance from P to Q. We'll use a symbol for that number that looks a lot like absolute value, but is slightly different looking. We pronounce that symbol as the length of the vector from P to Q, or the norm of P to Q, or the magnitude of P to Q. These statements are all equivalent to each other. This number is the distance from here to there. A vector quantity is also often described as being a quantity that has a direction and a magnitude. This is going to be the magnitude. To describe the direction, it's most convenient to have set up a coordinate system, which is what we've done here. If I use the coordinate axes as though they were rulers, I can think of how I travel from P to Q in the following way. I start at my initial point, and I travel 7 units to the right, and 3 units vertically, which will place me at the location of Q. Having set up a coordinate system, I could say that my vectors described this way go 7 to the right and up 3. There are many arrows that you could describe like that, though. I picked this point at random, and using a ruler, went 7 units sideways to the right and 3 units up. These 2 points are not P or Q, they are other points. I'll call them R and S. The distance from R to S is the same distance as P to Q, and R to S points along the same parallel line direction that P to Q did, or to be brief about it, the vector from R to S and the vector from P to Q have the same direction and the same magnitude. We'll call such vectors equivalent vectors. At times, it's going to be useful for us to be able to move a vector around so that its initial point is wherever we feel like putting it. Other times, we'll have reasons to leave the initial point of the vector at a certain fixed spot. This will depend on the application. Out of all such equivalent vectors, out of all such equivalent vectors, one of them has its initial point at the origin. In any of these earlier vectors that I've drawn in, to make the vector, you start somewhere, you go 7 units to the right and up 3. If you start at the origin, and to do that, you will go 7 units to the right and up 3, when we draw the vector in the position where its initial point's at the origin, we call that the standard position of the vector. Since we already know that in that case, the initial point has x equals 0 and y equals 0, to determine the vector, all I have to do is to tell you the coordinates of the ending point. In this case, that ending point will have x coordinate 7 and y coordinate 3. So I only have to tell you 2 numbers in order to tell you a vector if its initial point's at the origin. Looking again at this vector u with its initial point at the origin and end point at x equal u1, y equal u2, I'll describe the angle that the vector makes with the positive x-axis as angle theta. I'll use this for the direction of the vector. If we form this right triangle, we can immediately figure some things out. Firstly, I'll have angle theta there, a right angle there. Across the bottom is the first component of u. Vertically is the second component of u. And the length of the vector is the length of the hypotenuse, which is also written as the norm of vector u, or magnitude of u, and so forth. Because we know all about right triangles, we can immediately figure some things out here. Just based on the right triangle, we can figure out that the length of a vector is the square root of the sum of the squares of the components. Also, the cosine of this angle theta is the first component divided by the length of the vector. The sine of theta is the second component divided by the norm. And tangent of theta is the y component divided by the x component. Depending on which quadrant the vector points into, we can use an inverse trig function to figure out the actual value of theta itself. For example, if vector u has first component 5 and second component 7, I can use the preceding results to immediately state what the length of the vector is, what cosine theta, sine theta, and tangent of theta are, and then we can investigate obtaining the actual angle. Direct calculation shows that the length of vector u is radical 74, and then once I know that, cosine of theta must be 5 over radical 74, sine of theta must be 7 over radical 4, and tangent of theta must be the second component divided by the first one, 7 divided by 5. Because the vector points into the first quadrant, it's safe to use any of the inverse trig functions to find theta, so we'll do all 3 of them. My calculator is set in degree mode, so my answer will come out in degrees. Firstly, I'm going to calculate the inverse cosine of 5 over radical 74. Then I'll calculate the inverse sine of 7 over radical 74. Then I'll calculate the inverse tangent of 7 over 5. And if our thinking is right, I should get the same answer all 3 ways. Doing the work on the calculator, we see that we do get the same answer, and it works out to be about 54.46 degrees. This angle is about 54.46 degrees. You can also think about looking at the vector whose components are -3 for the first one and 1 for the second one. The Pythagorean theorem still applies. When I square -3, I get 9. Add 1 squared, 1 to that. The length of vector u is radical 10. When we calculate the angle, though, we have to be careful because of the behavior of the inverse trig functions. The inverse sine and the inverse tangent can produce angles that are in quadrant 1 or quadrant 4, but no other angles. The inverse cosine can produce angles that are in the first or second quadrant and no other angles. This angle is not in quadrant 1 or 4. It's not safe to use inverse sine or inverse tangent to get this angle. Luckily, though, it is into quadrant 2. Quadrant 2, using this inverse cosine, I will get the correct angle. As an illustration, though, what if I didn't notice that? The statements that sine of theta is 1 over radical 74, tangent theta is 1 over -3, and cosine theta is -3 over radical 74 are all true, but 2 of them out of the 3 will lead me to misleading results if I'm not careful. If I was careless, I would just say this. To see that there's trouble here, I'm going to calculate these 3 quantities using my calculator. The first one, incorrectly using the inverse sine, says that the angle is about 6.6 degrees, which is completely wrong because an angle of 6.6 degrees points off into the first quadrant. The second try, using the inverse tangent, again incorrectly, gives an angle of -18.4 some odd degrees, which is also wrong because you're not pointing into the correct quadrant. The thing that I get when I use the inverse cosine, though, is 110.4 degrees, which points off into quadrant number 2, which is what you want. The reason that it worked out this way is this angle isn't the inverse sine of anything, because inverse sine only gives you back angles in the right half of the plane. Same story for the inverse tangent. Inverse cosine is good in the first and second quadrant, and the vector you're interested in points into the second quadrant. So you do have to be a little bit careful about this kind of thing. We're going to define numerically a number times a vector in the following way. A number c times a vector u, literally c times the vector u1, u2 in component form. We're going to define it this way. We take each of the components of the vector and multiply it by the number. So I'm going to have a vector whose first component is c times u1 and second component c times u2. We more or less have an idea of what the length of that's going to be, but I want to do a calculation that shows that. The magnitude of c times u is the magnitude of this vector. The way we do magnitudes, we square the components, we add them up, and do the square root. Using elementary algebra, it's not hard to see that the magnitude of c times u is radical c squared times radical u1 squared plus u2 squared. This second quantity is the length of vector u. So this is going to be something times the length of vector u. If c is positive, radical c squared is just c. If c is negative, though, it flips sign. So if you want to be picky about it, which we do, we will write this as absolute value of c times length of vector u. This is pretty much what we expect. If the c is positive, say 3, this says that the length of 3 times u is 3 times the length of u. If c were negative 3, this says the length of the vector negative 3 times u is absolute value of negative 3, which is 3, times the length of u. So our expectation is satisfied. I'm going to think of having two vectors. The first one I'll call v. It has its initial point at the origin and terminal point at x equal v1, y equal v2. In order to go from the beginning to the end of vector v, or any vector equivalent to it, I have to increase the x-coordinate by amount v1 and the y-coordinate by amount v2. In a similar way, I'll have vector u in standard position. Starting at the origin, I go sideways u1 and up u2 in order to go from the initial point of view to the terminal point of view. The coordinates of this point, the point at the end of vector u in standard position, is x equal u1, y equal u2. What we're going to do is we're going to make a copy of vector v. We'll make a vector that is parallel to v, has the same length as v, but its initial point is going to be at the terminal point of vector u. Starting at the end point of u, x equal u1, y equal u2, as I travel along this clone of v, I must increase the x-coordinate by v1 and the y-coordinate by v2 in order to end up at the end of this copy of vector v. The coordinates now, not thinking about vectors, just the coordinates of this point. X is u1 plus v1, and y is u2 plus v2. This line is parallel to that line because these vectors are clones of each other. I could also think of starting at the origin and going out to the end of vector v1 in standard position. The coordinates of that point would be v1, v2. From the end point of vector v, I'm going to make a clone of vector u. Starting at v1, v2, as I travel from the beginning of this clone of u to its end, I have to increase the x-coordinate by u1 and the y-coordinate by u2. So if I went that route, my coordinates would look like this. But of course, u1 plus v1, this x-coordinate, is the same as v1 plus u1 because of ordinary arithmetic properties. u2 plus v2 is the same as v2 plus u2, so the y-coordinates are the same as well. If I travel out along u, then travel along a clone of v, or travel out along v, and then travel out along a clone of u, I end up at the same place. The coordinates are the sums of the components of the two vectors individually. For that reason, I'm going to think of the long diagonal of this parallelogram, which has components u1 plus v1, u2 plus v2. I'm going to define this to be what I mean by vector u plus vector v. If I think about going the other way, strictly speaking, I would write vector v plus vector u, but both of these start at the origin and end at the same point, so they're the same vector. So I know how to do a number times a vector. I know how to do the sum of two vectors. In an analogous way, I'll define u minus v to be u1 minus v1, u2 minus v2. There's one last piece of foundational information that I want to talk about. I'm going to call my vector w this time. Its components are w1 and w2. I'll still call the angle theta just out of laziness. We know how to multiply a number by w. We know how to find the magnitude of w. And we know some things involving the cosine and sine of that angle theta. I'm going to put these together and find something out. Presuming that w isn't the zero vector, so its length isn't 0, I can write w1, w2 this way. The length of vector w times a vector whose components are w1 over the length of w and w2 over the length of w. If that's not clear, think of multiplying through. Length of w times w1 over length of w would just be w1 again. Length of w times w2 over length of w would be w2 again, so you would get back the component form. The reason that I want to write it like that is those funny looking numbers that remain inside the sharp brackets, these are things we know about. w1 divided by the length of w is the cosine of the angle that the vector makes with the positive x-axis. w2 over the length of w is the sine of that angle. If w isn't the zero vector, then I can write w as a number, the length of w, times a vector whose entries or components are the cosine of theta and sine of theta. This is interesting for this reason. This number has only to do with how long the arrow w is. It has absolutely nothing to do with what direction it's pointing in. This vector depends only on theta. It depends only on the direction. So when we say that a vector is a quantity with length and direction, if I write it this way, that's really brought out. There's the length, there's the direction. One other useful fact has to do with that cosine sine vector. The magnitude of the vector cosine theta sine theta is radical cosine squared theta plus sine squared theta, but we have a trig identity that says cosine squared plus sine squared is 1, radical 1 is 1. If I write my vector w in this form, this is the length of w. This is a vector that's going to tell me about the direction, and this vector, the cosine sine part, always has length 1. So literally, this is the length times the direction only. If you know the magnitude or length of a vector and you know the direction it points in, this last fact will let me write down the component form. So I'll calculate the magnitude of the vector, the length of it, which is 8, times the cosine sine vector that goes with the vector r. The theta would be 57 degrees. I put the numbers into my calculator, and I find out what the component form is. We now know enough to answer the following kind of question. Instead of thinking of my vectors as being just displacements from a point P to a point Q, I can think of them as being forces. I'm going to think of a situation where there are 3 forces acting on an object. The first force has strength 20 pounds, and it makes an angle of 32 degrees with the positive x-axis. The second has a strength of 15 pounds and makes an angle of 170. The third is 25 pounds in strength, and it makes an angle of 247 degrees with respect to the positive x-axis. I want to find the total force. I want to find the sum of these 3 forces. I want to find its direction. I want to find its magnitude also. Another name for the total force is the resultant force. I'll give these forces names: vector F, vector G, vector H. The magnitude of F, G, and H are 20, 15, and 25 respectively, and the angle that F, G, and H make with the positive x-axis is 32 degrees, 170 degrees, and 247 degrees respectively. For each one of these vectors, I know its magnitude and its angle number, which, in view of what we were just talking about, will let me write down some formulas for these vectors. Each of the vectors f, g, and h can be expressed as a number times a cosine sine vector of the type we were just looking at. Of course, we know how to multiply a vector by a number, so we can work this out a little bit more. We're wanting to find f plus g plus h. The way we add vectors together is that we add corresponding components. So the first component of f plus g plus h is going to be this number plus that number plus that number. The second component of the total force, the resultant, f plus g plus h, will be that number plus that number plus that number. If I wanted to waste a lot of time, I would figure out all of those numbers individually on my calculator, carefully write them down, and then add them all up. But that's not what I'm going to do. I'm going to push the ugly work off onto the calculator. So I'll literally just type in the expressions for the 3 first components and add them together. According to my calculator, the result is about negative 7.5794. Now, if you don't know this trick for the Texas Instruments calculators, this is very convenient. I did this by adding those numbers up. I need to add these numbers up too, but the only difference between this calculation and that calculation is that I want to do sines instead of cosines. So here's a trick. I'm going to take what I've got on my screen, I'm going to push the second button and then enter, which brings up the most recently typed line. I'm going to back up with my cursor keys until I'm on the C of cosine, and then I'm going to push the sine button. I'll go over to the next one of the cosines and push the sine button, and do the same for the last one, and then press enter. This is the component form of the resultant force. This is an arrow whose length is going to indicate how strong the resultant force is, and whose direction is going to tell me what direction the object would accelerate in if it started at rest and was being influenced by these three forces. I am supposed to also figure out that magnitude and direction, so to finish this, we'll do that. Note that because my components are negative, I have to put parentheses around the negative component before I square it, or the sign will be incorrect. The magnitude of the resultant force is 12.3965 pounds of force to 4 decimal places after the decimal point. Vector r points off into quadrant 3. It is not okay to use the inverse sine, inverse cosine, or inverse tangent for that. But if you'll remember from your trigonometry, if I use inverse tangent, I need to then add 180 degrees to get the correct angle. So that won't be very difficult either. I'm going to be literal and type everything in, including the negative sign. After doing that, I find out that angle theta is 232.308 degrees. This points into quadrant 3, as it should. And lastly, if I start at the origin and I travel 1 unit directly to the right so that I'm at x equal 1, y equals 0, I can make a vector of length 1 that's parallel to the positive x-axis. We're going to call that vector I. I really should write the arrow above it, but sometimes I'll forget. Start at the origin, move directly upwards 1 unit of distance. This will be the vector with components 0 and 1, and I'll call that j. There is another commonly seen way of writing the components of a vector. Starting with the usual component form, because of the way we add vectors together, I can split it up like this. v1 plus 0 is v1. 0 plus v2 is v2. Because of the way we multiply numbers by vectors, I can write this first one as the number v1 times the vector 1, 0. v1 times 1 is v1. v1 times 0 is 0. Likewise, I can write 0 v2 as the number v2 times the vector 0, 1. 1, 0 is I, and 0, 1 is j. So if I write this, it just means the same thing as that. This looks a bit more like ordinary algebra, though. So to summarize, vectors are arrows. We get components by looking at the coordinates of the terminal point minus the coordinates of the initial point. Those numbers will represent with indexes 1 or 2, depending on if I'm on the x-axis or y-axis. There's another way to write that. It's the length of u times the cosine sine of theta vector. We have a third way of writing that. We have u1i plus u2j. We have formulas for the length of a vector. Cosine theta, sine theta, and tangent of theta can be useful for finding the direction. We know how to add and subtract vectors. We know how to take a number times a vector. This is everything that we know so far. In the next discussion, we'll take this up into 3 dimensions. It will turn out that almost everything works exactly the same. In the meantime, I hope everyone is having a good day. and I'll talk to you again soon.